Welcome to the second lecture video in our Class 16 series of lecture videos. Uh, in the first lecture video, we discussed what kind of conditions we could use to favor E1, which is a mechanism that's going on simultaneously whenever you have SN1 going on, operative. Alternatively, we could use a bimolecular elimination strategy to favor the production of alkenes. So what am I talking about? Here, this is another thing that's going to be difficult to wrap your mind around because now we're producing alkenes, but we're going through not a unimolecular mechanism, but a bimolecular mechanism, much more similar to SN2. And so let's say we have 2-chloro-2-methylpropane, tert-butyl chloride, and we throw it in water. If we just have water, that is our hydroxide concentration is 0, we will get an SN1 product, and then we'll get an E1 product. And of course HCl, which is dissociated, so we'll have Cl minus and H3O plus. However, if instead of having 0 basic conditions to start out with, we start out with a good concentration of hydroxide, so we're putting this in a basic solution of water, then we're not going to wait around and have enough time to go through an SN1 mechanism or form carbocations. That hydroxide is going to bump into this molecule, and we cannot do SN2 because we've got a tertiary carbon that's bonded to our chloride leaving group. Instead, we get an alkene, but now it's coming about through an E2 mechanism. So what is an E2 mechanism? Well, our hydroxide bumps into this molecule and it snags a proton from a carbon adjacent to the carbon that bears the leaving group. So in an arrow-pushing sense, it looks like this. It's a single step, it's concerted, and we form our alkene. Our hydroxide cannot access that tertiary carbon. It's just too sterically crowded. So instead, when it tries to bump into that molecule, it hits a proton on one of the adjacent carbons. And we form our alkene, water, and we kick out our leaving group, chloride. So let's see. Here is a molecular orbital description of what's going on. We have, our hydroxide anion putting electron density into the adjacent sigma star antibonding carbon-hydrogen molecular orbital, which is empty. And that helps transfer electron density to the sigma star carbon chlorine antibonding molecular orbital. And you can see that we have something that looks like a pi bond forming in the middle, right? A pi CC. As we pluck off that proton and put electron density in that antibonding carbon chlorine molecular orbital, which has the effect of breaking the carbon-chlorine bond. So what else can we comment about this? I drew this in a very specific conformational geometry for our 2-chloro-2-methylpropane. You notice that the chlorine and the hydrogen are in the same plane. They're in the plane of the page, and they are pointing opposite to each other, so you could describe that chlorine and that hydrogen as anti-paraplanar. And in fact, this transition state molecular orbital diagram cartoon is drawn in just such a geometry. And in fact, that is the low energy geometry for bimolecular elimination to take place. And so we need to look at that a little more in depth. And we might even consider a case that is different, but note the proton atom removed from the beta carbon, that is the carbon adjacent to the carbon that bears the leaving group, the chlorine, which is the alpha carbon, by the base is in the same plane as the chlorine leaving group. it must be anti-paraplanar. So this is a general, bond line structure for our leaving group X being anti and in the same plane as the hydrogen on the beta carbon. So X is bonded to the alpha carbon, carbons adjacent to that are beta carbons. Another transition state we might have considered would be the syn paraplanar transition state, and it's just that this transition state would be a higher energy transition state. It's not that bimolecular elimination cannot take place from this transition state. It's just that the activation energy for it is much higher than for the anti-paraplanar case. And of course, if the activation energy is higher by 1.4 kcals per mole, that leads to a 10-to-1 selectivity. By 2.8, that's 100-to-1 selectivity, in terms of differences in rate. And but interestingly enough, we will see an example where E2 goes through a syn paraplanar state because the molecule is locked such that the beta carbon hydrogen is syn paraplanar to the leaving group, and there's no way for it to access the anti-paraplanar state. So if you're stuck in that state, then yes, if you force the conditions, that reaction can occur. So a little bit more for this video, and I thank you for bearing with me on these lecture videos. A Newman projection for the E2 reaction mechanism can be useful for its transition state. That's what this little double cross means. So here we have hydroxide. Here we're plucking off that anti-paraplanar hydrogen on the beta carbon and kicking out the chloride as a leaving group to form our alkene, water and chloride. What you might see if you were drawing a Newman projection sighting down that carbon-carbon bond is, chlorine pointing straight down, and you'd see the hydrogen on the carbon behind our alpha carbon sticking straight up in an anti-relative sense. There's our hydroxide plucking that off. All good leaving groups for the SN2 reaction are good leaving groups for the E2 reaction. So, in addition to bromine, chlorine, and iodine, we have the sulfonates. So mesylates, tosylates, triflates are good leaving groups. I don't know if you recall, OMS stands for a mesylate. That would be, that oxygen bonded to this sulfur, 2 more oxygens, and a methyl group for our mesylate. So sodium hydroxide would do an E2, and we'd get our 2-methylpropene product out of this, as well as sodium mesylate, salt, and water. So that pretty much winds up this particular lecture video. I will see you for the next lecture video.